X-ray crystallography. Here's two photographs of crystalline substances. I forget exactly what they are. That's a snowflake. Don't remember what that one is. Doesn't actually matter, so why am I wasting time on it? Anyway, crystalline solids have a long-range order to their atoms or molecules. And that gives us these beautiful shapes that they form as solids. All of the little, I don't know, spires. This reminds me of Superman's North Pole place with all these spires of crystals. They all have the same shape. And it's not an accident. That's a reflection of how the atoms and molecules come together in a solid form. It's not an accident that all snowflakes have 6 sides. That has to do with how the water molecules arrange themselves. Yeah?
Was graphene a crystal in a way?
Graphene it would be considered a crystalline solid because the carbon atoms are arranged in a very specific pattern. Yeah. These are the sorts of substances we think of when we think of crystals, though, right? Beautiful crystals. So how do you figure out what the atoms or molecules, how they're arranged in there? Atoms and molecules are too small to see. So how do you even go about investigating that? You can use X-rays. So we've learned that waves can interact with each other and cause interference. You can get constructive interference, you can get destructive interference. And that works for all electromagnetic radiation. So constructive interference, the waves, the peaks line up with the peaks and you get a bigger wave. Destructive, peak lines up with trough and they essentially cancel each other out. Do you remember that double slit experiment, the guy with the box out on the beach? If you get light or any form of electromagnetic radiation passing through 2 slits, where the distance between the slits is similar to the wavelength of the radiation, you can get an interference pattern. So that guy did it with sunlight. You can also do it with X-rays. So atoms within the crystals of a crystalline solid have spacings of about 100 picometers. 100 picometers is about the wavelength of X-rays. So we can use X-rays and shine them through a crystal, and the gaps between the atoms act as the slits and cause interference patterns with the X-rays. So the X-rays interact with the crystalline lattice and we get this diffraction pattern. And by looking at the diffraction patterns and doing some pretty hefty geometry, you can figure out what the spacings are and the arrangements are of the atoms. Now you look at this pattern and you're like, ooh, that's pretty, but how the heck do you get this from that? Okay, that's well beyond the scope of this class. But we'll give you a little tiny taste of it. So if 2 waves that start out in phase have a difference in path length that's equal to an integral number of wavelengths, they will have constructive interference. They will come out being in phase. So what happens here is you've got these 2 rays. They're from the same source, so they are in phase. As they come in here, and the first ray hits the top of this atom and bounces off, it's reflected. The second ray penetrates through and hits the next layer and bounces off. You can figure out the difference in the distance that the wave traveled by looking at these angles. There's an angle theta. So we want n lambda, some integral number of wavelengths. That's going to be equal to 2a. The path difference is 2a. That's this distance right here. And you can derive that using geometry. Anybody want me to go through the derivation? No, I didn't think so. This is called Bragg's law. This could show up on an exam, not this next one, but a future one. But I would give it to you. I'd give you the equation. You need to know how to use it, though. N is an integer. a whole number, 1, 2, 3, 4, 5, etc. D is the distance between the planes, or the distance, the radius of the atom. Okay, that's the separation between these planes. And theta is the angle of incidence. So what they do is they take the X-rays and they shine it on the surface at a particular angle, and you look at the patterns that are emitted, and then you change the angle, and you record the patterns, and you just change the angle until you get constructive interference. So what they usually do is they measure the angle that gives constructive interference. So they get theta, the angle. You know the wavelength of the radiation, and n is an integer. So you can calculate the distance between the atomic layers. And this is one way you can find the radius of the atoms in that crystal. This is a sort of image that comes out of X-ray crystallography. X-ray crystallography is used for more than just looking at, pretty rock crystals or snowflakes. X-ray crystallography is what led to understanding of the structure of DNA. You've all heard of the double helix. Watson and Crick are famous for discovering the double helix structure of DNA. Their discoveries came from X-ray crystallography experiments. That's what gave them the clue as to what was going on. So it's also used for other biological molecules, proteins, enzymes, etc., as well as simple atomic lattices and different ionic compounds. So here's a sample problem. The spacing between layers of molybdenum atoms is 157 picometers. Calculate the angle at which 154 picometer X-rays produce a maximum reflection for n equals 1. So this is Bragg's law. So Bragg's law was D equals n lambda over, was it 2 sine theta?
Yeah.
Thank you. 2 times the sine of theta. So they're giving us some numbers in this problem. The spacing between layers is 157 picometers. What variable is that?
Wavelength?
It's not the wavelength. It's D. D is the distance between the layers.
So we'd be finding theta.
Yeah, we're finding theta. So calculate the angle. The angle is theta. And the 154 picometer X-rays. This is the wavelength of the radiation. So I didn't plan this out very well, but that's lambda. And then they're saying do it for n equals 1. So what we need to do is rearrange this equation. So we get 2 sine of theta is equal to n lambda over d. And I got that by swapping the numerator on one side with the denominator on the other side. It's the same as cross multiplying and then dividing. And then I need to get rid of this 2. So I'm going to take that 2 away and put it over here. So I get sine of theta equals this. So we can calculate that. Oh, good. My calculator's in here. So let's plug our numbers in. N is 1. Lambda is 154 picometers. 2 is 2. And D is 157 picometers.
Does it matter what it's in picometers, or does it have to be?
Excellent question. What do you think?
As long as you cancel out.
As long as the units are the same, they're going to cancel out. So excellent question. Does it matter what unit you use here? No, it doesn't, as long as it's the same unit for both the distance and the wavelength, because the picometers cancel out. So I've got 154 divided by 2 divided by 157, 0.49, 0.44586, no units. That's what the sine of theta is. And anytime you're using functions like sine or logarithms, keep extra significant figures, okay? Because a small rounding error can cause a big error when you invert the function. How do we get rid of sine? You can't divide by sine. You have to do inverse sine. And your calculator should have a button. So theta is going to equal, they do it like this, the inverse sine of that number. So inverse sine, bring the answer
So it has
back
to be
to.
in degrees, right?
Yeah, this is going to be degrees. So it gives us all of this mess, and that would be degrees. In chemistry, we're not going to use radians. We're just not. Leave that for the mathematicians. Now, you know, is that a reasonable number of significant figures there? In terms of measuring an angle? Do you think you can measure an angle that precisely? It's probably a bit ridiculous. On a multiple choice exam, though, you get that number, and then you can pick the one that would round to. I would kind of guess maybe 0.513 degrees is probably close enough, maybe even 0.5. We're not going to worry about sig figs when we do sines. Yeah? How did I put that in my calculator? That's an excellent question. Okay, my calculator, the 36X Pro, I put in the function first. So the sine to the -1, and it's not, you can't do the exponent thing. There is a button that should be sine to the -1. And then I type this number in after that and press equals.
I feel like 29.
Oh, are you in radians?
Yeah. I got
Okay, so not sure how this happened. My calculator's in radians. I thought 0.5 was a weird angle. Yeah, thank you. Because I screw up, and I've already screwed up multiple times today, and I think it's going to continue happening. So just keep me on my toes, please. Okay, let's do that again. No, that's not what I want. There we go. Wrong.
How do you change the calculator out of that?
That's an excellent question too. How do you change your calculator out of radians? This goes on and on and on. I'll probably call that 29.4 degrees. On my calculator, there's a mode. So you press mode, and that gives you all these different options. This is why it's really important to be using the calculator that you're going to use on the final exam during the semester. You can't use a programmable calculator on the final exam. That's not my rule. That's the American Chemical Society's rule. They make the test. They make the rules. Yeah, and just not even knowing that your calculator is programmable and claiming not to know how to program it, unfortunately, isn't good enough. So, any other questions?
Isn't any graphing calculator?
Not really, no.
That one is the one you have. Yeah, that one is.
Yeah, so the 36X Pro has a solver in it. So, you can solve equations, but it's not considered a programmable calculator.
The one you have is.
The issue with that is that a student could record the answers to the standardized exam and publish them or share them with other people. And so it's security for the exam, not cheating by you as an individual, is the reason that we can't allow programmable calculators.
So how do we figure out if our calculator is
How do you figure out if your calculator is programmable? Probably the simplest thing is to show me and ask me.
Okay.
Yeah. Okay, so moving on, we can talk more about that in lab.